So good morning from the Hellenic Mediterranean University International Relations Office. Welcome to one more Sci Cafe. It's a great pleasure to have with us a distinguished scientist, a Greek scientist that works on abroad with, an impressive, I would like CV. I would like to thank first of all, Panos Polygerinos for the introduction. It's a great pleasure to have with us Dr. Alexandros Gerakakis, who is a senior researcher and technology associate at the Luxembourg Institute of Science and Technology. Before Alexandros joined this institute in Luxembourg, he has an impressive CV, I would say, a very nice curriculum of studies. He obtained his bachelor degree from the School of Applied Mathematical and Physical Science in the National Technical University of Athens in Greece. He received his master's degree, I'm very pleased about this, from the University of St. Andrews in photonic and optoelectronic devices. He holds a PhD in physics from the University College London, and since then he has been a postdoc in very famous universities, including Harvard. He was an associate research physicist at the Princeton Plasma Physics Laboratory and an assistant professor at the Aerospace Engineering Department's Texas A&M University, where he led the optical probing and manipulation group. So Alexandros, thank you again for your kind acceptance and contribution to our Sci Cafe. I'm very happy that you're in contact with our leading scientists in laser plasmas activities here in Crete, Professor Tatarakis, and we are going to be very happy the next talk to happen face-to-face here in Crete. The floor is yours for the next 40 minutes. Thank you.
Thank you so much for the introduction and for your kind words, and it is indeed my pleasure to be here and to talk to fellow Greek scientists. That's always nice. And of course, thanks to Panos for making the introduction. So I just want to discuss today how we are how we're moving towards replacing mechanical metrology tools by using lasers. Always the answer to any problem is lasers. So that's my standpoint. Why is this not working? Okay, it's working now. So as you mentioned, I was an assistant professor at the Aerospace Engineering Department at Texas A&M University up until almost a year and a half ago. And since then, I transitioned to the Luxembourg Institute of Science and Technology, where now we're setting up our whole activity. That being said, before I start, if you know of anyone looking for both a PhD or a postdoc, we are looking for people, and this is in relation to the work I'm going to discuss about today. So if you know of people that would be interested in that, they should contact me directly or visit the job postings at least.lu. So before I start, I would like to acknowledge my group at Texas A&M for the work that we did there, and part of which I'm going to discuss about here. Also my collaborators, as well as the funding agencies for, again, the work that is going to be presented here. So I'm going to start by briefly outlining our motivation, what is the technique that we're utilizing, and what is the experimental setup that we're using. And then I'm just going to briefly discuss and showcase the activities we have done in utilizing these techniques for different measurements in plasmas and neutral flows. So the first question is, why do we even care about metrology, and what is metrology, and why is this important? And in the global view of scientific understanding, where you have an interplay always between modeling theory and experimentation, where one feeds into the other, you always need to have the correct tools to assess and validate all the other tools. So as experimentalists, we need to have the tools to accurately measure in situ and validate and verify both simulation and theories, so that we can then progress the scientific understanding and ultimately bring science and society forward. Now, since we care about metrology, why should we even care about flow metrology, and what is flow metrology? I think the best illustration of why we need to care about that is the kangaroo route in 1947, which meant that if you want to go from Sydney to London in 1947, you had to spend 55 hours with I don't even know how many stops in order to make that transition. Now, So the idea is always to be able to go faster, cheaper, and better in NASA's terms. And the thing is that we understand many things in general in science nowadays, but we don't understand many key things and very classical things about flows. And in the words of Richard Feynman, the biggest of those is turbulence, which is the most important unsolved problem of classical physics. And my favorite quote is by Horace Lamb, who says that I'm an old man now, and when I die and go to heaven, there are two matters on which I hope for enlightenment. One is quantum electrodynamics, and the other is the turbulent motion of fluids. And about the former, I am rather optimistic. And he's exactly right. We know so much more about quantum electrodynamics, actually because of the work of Richard Feynman, but we almost don't know anything about turbulent flow in both neutrals and plasmas. So the question is, how do we tackle this problem? And of course, I'm talking about plasmas. This is also important if we think about Hall thrusters, arc jets, or NASA AIMS, arc discharges to create nanoparticles, DBDs to also create nanoparticles, sputtering for nanotechnology. These are big questions that we currently don't have good instrumentation to understand what's going on in these processes and how to diagnose what goes on in there and actually provide with feedback and create better understanding. So if we're talking about flows, we need to always know three things in every flow that we have. And that is the temperature of the species, the density of the species, and the flow velocity. And when I'm talking about temperature here, I'm mainly talking about translational temperature and not raw vibrational temperatures or electronic temperatures. So if we then want to create the best diagnostic about flows, we need to start with a Gedanke and think about the best characteristics that we would want it to have. So the first one would be for it to be non-perturbative. That means that we would not alter the properties of whatever it is that we're measuring. Then we would need it to be single shot. So that would allow us to perform very fast diagnostics, such that even if we have fast transient environments, we can measure accurately. Ideally, we would want it to work with all species, such that we can diagnose different environments. Then we would need it to work in situ, allowing us to measure in plasmas, fires, combustion, explosions, wind tunnels, everything. And ideally, we would want to map out as much of the flow field as possible. So let's see where we are today and what is the state of the art. The state of the art is practically this one. It's not dissimilar to the Pitot tube that was invented by Pitot in 300 years ago. And it was made to measure the flow in the Seine River. And as you see today, still, you see it in airplanes today. It's this removed before flight. This is the Pitot tube. This is on a Dassault. I know Greece bought some Dassault airplanes. So these are what you have in front. In Formula One cars, this is the state of the art in understanding flow around species, around structures, sorry. Another way is using particle image velocimetry, which of course is intrusive, as can be easily seen. This is a Mach 6 wind tunnel from Texas A&M, and you can see that still we're using a wing wire, a hot wire, to measure the flow. And you can actually see how the boundary layer of the hot wire is perturbing the boundary layer that we want to measure. And we're talking about plasmas, then Langmuir probe is still dominating. Where it's also a very invasive technique where you practically are sticking the probe within your plasma and you measure it. And clearly you're altering the plasma by doing so. So as I said earlier, the answer is always lasers. And since the lasers were invented, the first thing to do would actually to shoot a laser through any gas or plasma of interest and see it scattering. And in that case, you just shoot the laser through your, let's say, your gas, and you collect the scattered photons, and from that you create your measurement. Now, things are becoming much more complicated if you have here an optically noisy environment, such as a flame. So in that case, how can you distinguish the photons that are of interest to you to the photons coming from the optical background? And this has been a problem since the invention of the lasers. And of course, there have been a myriad of different techniques trying to actually solve this problem and be able to measure accurately in optically noisy environments and derive all the quantities that I mentioned with the characteristics of an ideal metrology tool, as I mentioned. And now, so with that introduction and that motivation, I can actually start discussing about how it is that we are approaching this problem, and it is with a coherent Rayleigh-Brillouin scattering. And here I'm just going to explain how this works. So imagine that we interfere two laser beams in a medium, which we are calling the pumps, and they're interfering, let's say, in air. So I can do this experiment here, and I have two laser beams, intense laser beams interfering in air. So now the oxygens and the nitrogens in air are going to see an electric field landscape of high and low intensity nodes within the medium. So they're going to feel, due to the optical dipole force, they're going to feel an attraction towards the high intensity nodes of this interference pattern, and then they're going to start populating it. So then that creates a periodic density modulation within the medium. Practically, I am engraving a Bragg mirror within whatever medium it is that I am using. Now then, from a Bragg mirror, I can always Bragg scatter, and that's exactly what I'm doing. I'm sending in a third beam, which I call the probe, incident at the Bragg angle on this periodic density perturbation, which instead of going straight is actually being Bragg deflected, giving rise to a fourth beam, which I call the signal. And that's exactly the beauty of coherent Rayleigh-Brillouin scattering. The fact that I'm creating a signal beam, which is another laser beam, emanating from the point of measurement and can escape away from the point of measurement. So I can think that I can make this experiment this measurement in a fire, in a plasma, in an explosion, and the optical background is going to be scattered in 1/r², while my signal beam is always going to be maintained as a laser beam. That means that it's actually beneficial for me to put the detector as further away as possible, since the SNR is going to increase rather than decrease if I do so. So this is the big advantage of CRBS. So now, up until now, I have assumed that the frequencies of my two pumps are exactly the same, being at frequency f, and that would create a standing wave within the medium. Now, if I introduce a frequency difference delta f between a relative frequency difference delta f between my two pumps, then I'm actually going to be creating a moving lattice, a lattice that moves at a certain velocity. Now, by doing so, I'm interacting with the particles of the velocity distribution function that have the same velocity as that of the lattice. So by changing the delta f between my two laser beams, I change the velocity of the lattice, and then I'm interacting with different parts of the velocity distribution function. So then, if I measure the intensity of my signal beam with respect to the velocity of the lattice, I can actually map out directly the velocity distribution function that I'm interrogating. And from that, I can derive all the quantities of interest. So this is exactly what we do in CRBS. We are changing the velocity of the lattice, we're interrogating the velocity distribution function, and measuring the intensity of the signal beam. And if we do that, we get this Batman line shape that we call, which is the summation of three peaks. The first one is the Rayleigh peak, which is exactly a representation of the translational temperature of the medium, and the two Brillouin peaks due to acoustic waves that we're launching within the medium. So from this line shape, I can immediately derive the temperature, the density of the species, the speed of sound, the viscosity, and the polarizability of the species. And as I said, I can do that in a coherent laser beam that's emanating out of the point of measurement. Now, the features that I'm going to see are a function of the so-called Y parameter, which is a function of the wavelength of the lattice over the mean free path. And this is how historically it has happened. So here we can only have at very low values of the Y parameter, we can have just the Rayleigh peak shown here. At medium values, we have the CRBS, the free CRBS spectrum, while at very large values of the Y parameter, we only get the Brillouin peaks shown there. And we can access all of those regimes just by changing the crossing angle of our pumps. Now, the problem up until 2013 or 2012 was that if you wanted to make a CRBS measurement, there was one way in doing it. You would buy two commercial lasers, two standard, lasers from Continuum or from Spectrophysics, with two commercial seeders, and you would reference the two seeders to each other, keeping the same frequency between each other. And then you would keep one fixed and change the frequency of the other in order to change the velocity of the lattice and obtain these things, these spectra. Problem was that it would take, and it wasn't just me. I mean, I did this here, but other people all over the world were doing the same experiments. It would take everyone 10 to 20 minutes to obtain one spectrum. So that was pretty useless for CRBS, because if you wanted to measure something fast, then you could not use it. And the problem was that we were using constant velocity lattices. So as I mentioned, we change the velocity of the lattice, measure the intensity of the signal, change, measure, change, measure, change, measure. And that would take forever to obtain a spectrum. I can tell you that for this paper, I spent 26 hours in the lab in order to obtain all the spectra that I needed. So that shows you how bad that method was. So I decided to change that then by using a Chirp lattice. So instead of using constant velocity lattices and measuring, we used lattices that would address all the velocity components that would result in a CRBS spectrum within a laser shot. And that's exactly shown here. So within the duration of the laser shot, we have all the velocity components that would give me a CRBS spectrum. And this is exactly shown that now I have my CRBS spectrum on my oscilloscope in a single laser shot of 200 nanoseconds. And now I can actually use CRBS for faster phenomena, for stuff that happen faster than, slower than 200 nanoseconds. And this actually enabled a variety of studies to be done with CRBS. So now a CRBS is highly localized, gives a laser beam signal output. It allows us to resolve much lower densities than your standard Rayleigh-Brillouin scattering, and it is now single shot as well. So here, and just to show that, for example, it can work with both molecular and atomic gases, I took these scans with respect to pressure. It took me 5 minutes each per data set versus the 26 hours that I said earlier. So now I can actually utilize it to do a multi-parameter study of many things. So I'm going to briefly discuss about how we do this. So we start off with a master laser, because the bad thing with CRBS is that it's not commercially available currently. I am working towards changing that, but we have to design and build our own lasers. So here we're starting with a standard vanadate crystal, Neodymium vanadate crystal. So here we have a 5mm cavity and the output coupler here. But what we are introducing is a lithium tantalate electro-optic modulator in intracavity. So what we're doing to that, we are applying voltage, and by applying voltage to the EOM, we're changing its refractive index. By changing its refractive index, we're changing the cavity length. And by changing the cavity length, we are changing the frequency of the laser output. Now, the problem with neodymium lasers is that once you change its operating conditions, their intensity tends to fluctuate in what is called the relaxation oscillations. And that would result in our lasers to be doing that in the intensity domain as well. So we are interested in keeping the frequency information while disregarding the intensity information. So what we're doing is that we are injection locking the master laser onto a slave laser, which is a diode laser. So we're forcing the slave to emit at the same frequency as the master while keeping its intensity CW, stable. Sorry. So then we are further amplifying that through a commercial fiber amplifier and split the output into two EOMs, which are just Mach-Zehnder interferometers, that would allow us to perform pulse shaping. So what we do here is we open up first this electro-optic modulator to form the first pulse. And at a later time, we open up the second EOM here. But when we open this EOM, we're sending in a voltage signal to the EOM in the master laser, such that the second pulse has a frequency relation with respect to the first one. So then we are introduce the created two pulses at the exact same time, which have got a frequency relation with respect to one another. And the beauty of that system is that it's a self-reference system. It's not two seeders and referencing one seeder to the other. This is a self-consistent system within the 500 nanoseconds that are performing this operation. Then finally, we are further amplifying that with an amplifier stage. Currently, we're using 4 amplification stages. And then we are sending in the beams to perform CRBS measurements. So what we can do here, this is an example of the chirps that we can create with a laser. This is the heterodyne signal extracted here. We can also change the relative time difference between the two pulses, and also change their chirping rate. And we can also even change the pulse duration, and change the pulse shape, and change the chirping rate between all the lasers. And this is just a CAD drawing of the laser that we have built. This was my lab at Texas A&M, and this is the laser system shown behind. So currently we can achieve approximately 500 millijoules per pulse, 10 gigahertz chirp rate for the two beams. Pulse durations from 10 to 1,000 nanoseconds, and the standard repetition rate of 10 to 30 hertz. And of course, we are keeping on working on expanding the capabilities of the system. Now we have actually brought this system into Luxembourg. It's in my lab in Luxembourg now, and we are making it work here. So now I'm going to change gears, and I'm going to discuss about how we have used single-shot CRBS to perform different types of measurements. The first one is the in-situ measurement of nanoparticles. So here, we can create nanoparticles in an arc discharge by ablating the graphite anodes and cathodes of the arc discharge. The problem is that this is a super violent process and a super bright process. So any type of laser diagnostic is very hard to work here. So the idea is to actually be able to measure in situ the nanoparticles and derive their properties such that we can backfeed it into models and understand the process better. And that was work done at the Princeton Plasma Physics Lab. So the idea there was to use single-shot CRBS in order to measure nanoparticles in the arc discharge. And Michael Schneider, my collaborator from Princeton, he had the fantastic leap forward of actually now, for the optical lattices, not to populate them with oxygens and nitrogens, but actually with nanoparticles, and measure the signal from the nanoparticles. And here what it shows is that because the polarizability of, for example, C60 is much larger than argon, I think it was in this case, then the signal would be dominated by the presence of C60. So here, because we don't have the density to support Brillouin peaks in nanoparticles, what we will expect to see is only the Rayleigh peak, from the height of which we can find the relative density of the nanoparticles, and from the width of which we can find their mass, if we know the temperature at the vicinity. So just to illustrate how important it was to do the single-shot CRBS, there were studies showing that the nanoparticles are flying out of the plasma region at the velocities of 100 meters per second. So we only had like a 1 millisecond of residence time to perform this measurement. So we need to be faster than 1 millisecond. So single shot was ideal. And here, this is just to illustrate, this is the arc discharge that was creating the nanoparticles. This is imaged through an ND filter of 14. So you can imagine how bright the source was. And here you can see how violent the process was. So any type of light scattering was super challenging in such noisy environment. So we started by doing a standard CRBS geometry, such as the one shown here, where the two pumps are kind of propagating each other. So this is pump 1 and pump 2 are coming through here. Then the probe is coming in at the same wavelength and is derived from one of the pumps, is coming in at the Bragg angle, and then the signal beam kind of propagates pump 2. The problem is that doing this measurement in nanoparticles has a lot of misscattering emanating from the propagation of pump 2 within the arc discharge. And that brings in a lot of background in the line of sight of my 3D boxcar geometry shown here, where the pumps are on one plane, while now the probe is coming in at the plane orthogonal to that of the pumps, such that now our signal has no interference from any scattering in its line of sight. And this actually made it work, and we did perform measurement of nanoparticles of less than 10 nanometers in the arc discharge. And as I said, we measured the mass, and we knew the temperature, so we can derive the dimensions, making some assumptions. And this is the first type of measurement of nanoparticles in situ in an arc discharge. And to the best of my knowledge, this is still the only way where you can perform such a measurement. Now, so this was done for nanoparticles. Now I want to discuss about how we measure the velocity of neutral flows. If we think, so far I have considered just stationary gases and measurements in stationary gases. But if we now think that we have some gas flow, then we expect to see some Doppler shift of the Rayleigh-Brillouin scattering, of the Rayleigh-Brillouin line shape. And this has been showcased with techniques such as filtered Rayleigh scattering, but it has never been shown with CRBS. And of course, CRBS has the advantages I discussed earlier with respect to filtered Rayleigh or other Rayleigh techniques. The idea here is that we would be able to measure velocities as low as 3 to 5 meters per second in much lower gas pressures as low as sub-torr. And here, if we think about it, if we think how much is the Doppler shift that we expect to see, so here we can expect that for a flow of 10 meters per second, we would anticipate a Doppler shift of 20 megahertz. And this is another important characteristic of CRBS. The fact that we're performing a spectroscopic measurement, but now we're doing that in time. So we're measuring in the oscilloscope. So every signal we see is on the oscilloscope, and the oscilloscopes are measuring in time. And they are much easier measurements to perform versus performing them in the frequency domain. So here, just by knowing that this chirp here is 1.5 gigahertz over 150 nanoseconds, it means that I can resolve a Doppler shift within 2 nanoseconds. So if I see my whole line shape shifting by just 2 nanoseconds, then I immediately know that I have a velocity of the flow of 10 meters per second. So I can use then as a very standard photodiode to do that. You can find that commercially, and hence we estimate minimum velocity resolutions down to 5 meters per second. Actually, now we estimate even lower resolutions. So in order to prove that, we did an experiment in my lab where we had a compressed air coming from the building, and we had 2 flows like that. This is the optical lattice. So we would turn off the gas flow, and we would expect to see the line shape here in green. And then if I turn on the flow from one side, I expect to see the line shape going one way. And if I turn the flow on the other side, then I would expect the line shape to go the other way. And this is exactly what we did. So no flow here, and we turn on the flow, we see it going one way on the oscilloscope immediately. And then we turn it off, and then we turn on and we see it going the other way. And then I close it and I can see it again. And here again goes the other way. So physics works, and I can actually use single shot CRBS to perform gas flows measurements as well. And that's exactly what we did. And we benchmarked it versus a pitot tube, so versus the state of the art. And now we can see that we can have both in air or CO2 or whichever gas we put there. We have almost 1-to-1 comparison between the pitot tube and CRBS. So now I can actually use that in a wind tunnel, in the NARC jet facility, anywhere to perform flow measurements without being obstructed by the optical background. So in order to improve the state of the art of CRBS, up until now, we have been using probes at the exact same wavelength, but we decided to go to a 2-color CRBS scheme where now the probe is at 532. And now the Bragg angle is at a funky 30 degrees, but still it allows me to go to much lower densities and much better resolutions. Owing to better technology in detectors, I can spectrally filter the pumps, but also because of the lambda to the -4 Rayleigh scattering, I obtain immediately times 16 improvement in my measurement. And this is just showing how indeed from going from these densities, then I can go actually to these tails here that with a new system. So then we used that in order to measure neutrals in a glow discharge. And why glow discharge? This was the first time that CRBS was applied in plasmas systematically to measure properties within the plasma. So we decided to start off with the simplest one, which is a glow discharge, and measure because it's super stable, and measure the neutrals within the glow discharge. And why the neutrals? Here, in a glow discharge, the ionization ratio is as small as 10 to the minus 4, 10 to the minus 6. So whichever signal we would see there would be coming from the neutrals. So the idea would be to radially scan the glow discharge and measure simultaneously the density and the temperature of the neutrals within this glow discharge using the two-color CRBS scheme. Now, in order to perform this measurement, we designed a new chamber and we implemented it as shown here. Again, this is the funky 30 degrees angle I mentioned earlier from the probe. So we had to really do some custom solutions here. Nevertheless, we did it. And this is the arc discharge in the center. So the beam would come here in the center and then would scan radially across. Now, the problem with four-wave mixing techniques is that they measure at a point. So if we want to scan radially, we would either need to shift the beams or shift the chamber. So in this case, it was easier to shift the chamber. So we devised the whole mechanism to be shifting the chamber with respect to the measurement point. And the idea would be to measure at different points across the discharge and obtain these measurements there while moving the whole chamber. So the assumptions here is that we have got a positive column that it's radially symmetric, and that's almost a valid assumption. And the other one is that we have got at each time we were performing the measurement that we had the exact same glow discharges. Now here we're talking about xenon at 15 torr, so we are not expecting any brilliant components. And here again, as was the case with nanoparticles, the density would be derived from the height of the curve, while the width would give me the temperature since I know the mass. And that's exactly what we did. So we sat at the center of the glow discharge and we started cranking up the current. So these are all single shot CRBS spectra. And you can see that if I normalize the unity, I'll start off with what a Rayleigh distribution I would expect. And then immediately I see the width changing, which means that I can immediately measure a temperature change from this width change. Whoop, sorry for that. Yeah. But now if I normalize with respect to the first curve, I can see that the density drops quadratically as I would expect from a nonlinear process. And then I can actually use that as a density measurement as well. So simultaneously, I can measure both the temperature change and the density change as I would expect from, as shown here, by changing the current in the glow discharge. So then, as I said, we would radially scan across the discharge, starting from the center. So 0 point here is the center, and we derive the density and the temperature between the two. Here, notice how when we did this measurement at different days, we wouldn't get the exact same line shape, but and that is because the assumption is that at each point we have the exact same, at each day we have the exact same glow discharge. But definitely there is a trend in both the density and the temperature as we perform this measurement. And indeed, we were able to derive measurements that are in agreement with those found in the literature. And we're now actually running a simulation to exactly validate those measurements and move on from there. So, and with that, I hope I convinced you that single shot CRBS is indeed a great tool to measure simultaneously density and temperature measurement of neutral species in a glow discharge. Now, coming back to the ideal characteristics of every diagnostic, CRBS has not yet been shown in a highly ionized plasma. And I'm not talking about a glow discharge, but I'm talking about an arc discharge, to be able to measure ions in an arc discharge, for example, or a capacitively coupled discharge or something else. Also, as I mentioned, the bad thing was that we had to scan the whole chamber in order. We received a grant over the last year from the FNR in Luxembourg in order to actually move on the state of the art of CRBS. So the idea here is to be able, within a single laser shot, to measure simultaneously across the whole profile with CRBS in a single laser shot. And that would allow us to measure nanoparticles across this boundary. It would allow us to measure the boundary layer in a single laser shot. It would allow us to perform the exact same measurement, not in a point fashion, but rather in a line fashion. So going from a 0D CRBS into a 1D CRBS. And that would indeed bring to the state of the art in a much better position. Also, here, another thing we want to do is to, for the first time, measure the ions in an arc discharge or in a capacitively coupled discharge and be able to perform ionic measurements of these species and actually be able to separate both neutrals and ions from these measurements. And to conclude with coherent Rayleigh-Brillouin scattering, I hope have convinced you that it's a very nice non-resonant four-wave mixing technique for measuring temperature, density, speed of sound, flow, velocity, viscosities and polarizabilities of neutral and plasma species, and it's great for both gas and plasma flow measurements. And it works with almost every gas, and which can be an advantage and disadvantage, and I would be happy to discuss that even further. And just 3 more minutes, I want to, and of course it's time to replace the mechanical probes because they are not good. And I just want to also bring your attention to a new paper that came out last month, which is about using similar techniques, but now for electronic measurements, for measurement of electronic temperature. So now the idea would be create the same optical lattices, but instead of using, instead of measuring the ions and the neutrals, populate the lattices with electrons and scattering of Thomson scattering from them in what would be coherent Thomson scattering. So obtaining the electronic measurement, the measurement of the electronic temperature within, again, a single laser shot, with the advantages of doing that coherently versus, standard Thomson scattering, and obtaining an electronic temperature of like that using the optical lattices. And I think with that, it's time for me to conclude. I would leave you with a time lapse of us building the laser in Texas, and I would take any questions.
Thank you very much, Alexandros, for this very nice presentation. Now the time is, the floor is to the audience in case that there are questions to the speaker. Before, the questions comes from the audience, I have a question, a naive question, because I don't know. So from the beginning of your lecture, what did you understand is like you are creating a grating within your material, and then based on the scattering, the characteristics of the optical signal that is your scattering signal, you can identify and you can mine properties about the material you have excited with the pump pulse. Am I right? So my question here is the following: in order to observe this Bragg scattering, it's very essential also to define the period of the grating, that in your case is the material. So how stable? I'm sorry, Alexandros, please.
So here we're talking about gases, right? So practically the period is defined by the crossing angle of my pumps. So it's actually the period of an interference pattern. So I'm just arranging the oxygens. So if I do the measurement here, I'm arranging the oxygens, I'm compressing and decompressing. Practically that's what I'm doing. At the high intensity regions, I'm compressing and decompressing at the low intensity. So practically that creates a refractive index contrast that I can use as my Bragg mirror, if you may.
All right. So this happens before the laser arrives, no? Compression and
this happens from the laser. So
from the pump. Here. All right. Okay. Yes. All right. Then. All right. So this generates the period of your grating, no?
Yes, exactly.
All right. So and how stable should be the probe in order to identify, from your signal the whole information as a laser? How stable it should be?
Stability in terms of what?
On terms, for example, of the wavelength, emission regarding, this kind.
Actually, you don't care. The probe can be whatever wavelength it needs, so long as it is incident of the Bragg angle. So it's no. So the Bragg angle is the only thing that.
All right. So because it is like ML equal D sine theta. This is what I know.
Yes,
so the D,
exactly.
the D comes from what you are doing with the pump in order to arrange the period of the grating. But then the lambda comes from the probe, in order to check the scattering. So lambda Of course, also you have the order of diffraction that you measure, but this defines
but you
also
always
the
go
angle.
on the yes.
All right,
you go on
got
the
this.
first order.
But the wavelength is there. So
Yes.
how?
So it's exactly the same thing that you do in Bragg scattering in crystal, right? So you have
Exactly
the crystal, the D is here, the crystallographic distance is set by the interference pattern. And then the X-rays, the wavelength of the X-rays is here, the analogy is the probe, the wavelength of the probe. And I can use whatever wavelength I want. And then I can back calculate the Bragg angle that I need to shine my probe on this gradient.
Okay. Thank you. Thank you.
Can I have two fast questions because I have to leave.
Of course. Go ahead, Michalis. Go ahead.
Thank you very much for your nice presentation. Very nice indeed. The first question is related to the probe beam. Why are you using the same wavelength and not a different wavelength so that you avoid the self-scattering of the other beams? And
no, that's a great question. So if you think about it in terms of single shot CRBS, the only requirement that you have of the probe is that it should be of the same time length as of the same duration as that of the whole lattice, because you need to illuminate different parts of the lattice. So you need to have, a flatter profile across this whole lattice, right, in order to obtain stuff like this. So the reason why we did it like that here is that because it was simple. You just let me actually show it in the nanoparticles. So here it was actually simple to derive, to get an orthogonally polarized probe of the same duration as that of the lattice, and to do it like that. But you're absolutely right. We did that because it was simple. Nowadays, we extract the same thing, but now we take it through a second harmonic generator, and then we make it the green, and then we have the same duration, but now in green, and we are coming in at the Bragg angle of 30 degrees, and then we don't have those issues. Yes.
Okay, Alexandros, thank you very much. And the second question, I'm not sure if I have understood correctly. In one of your last slides, you put an X on plasma diagnosis with coherent Rayleigh-Brillouin scattering. Is this because of the self-radiation of the plasma?
No. Actually, as I showed, in the arc discharge, there is that's the thing with CRBS. You don't really care about what's going on in the background. You can imagine that in my lab, we put the detector 30 meters away from where we are measuring. Because again, all the background, all that emission is 4 pi scattered, while we have a laser beam. So if you go further out, the further out you go, the more the background has dropped, while your signal remains a laser beam. The only reason that it hasn't been done in plasma is that no one ever tried it. That's the only answer. And it is in my immediate plans to do that.
So Alexandros, thank you very much indeed. I have to go now for the PhD examination. So I hope that soon we will have the opportunity to speak.
I would be more than happy.
And you are invited to come to the IPPL whenever you have free time. We can arrange this.
We should definitely arrange that. And thanks for the invitation.
Thanks very much. Thank you.
Thank you.
And also we have a comment from the Vice Rector of the university, and also part of the IPPL, Professor Nektarios Papadogiannis. Very nice talk. Professor Papadogiannis is an expert in pulse lasers, and not only this. Very interesting results, and with possible common ground for collaboration. They have to leave because they have this PhD viva right now. Okay, Alexandros, this was like very nice presentation. I will upload this to the YouTube channel so more people to be able to watch it. And we hope to see you again, not again, but to see you live in Crete. It will be very, very nice.
No, we should definitely arrange that. Thank you.
Thank you very much.
It was my pleasure.
Thank you. Thank you very much, Alexandros. Bye.
Have a great day. Bye-bye.